Welcome back. Today we will discuss about vision transformer. So let's start. First, what is vision transformer? So vision transformer is a kind of a neural network architecture that processes images and it understands images for different purposes. For example, we can use it for image classification, even object detection, and even in generative AI, we can also use vision transformer. So basically it is proposed back in 2021 in a conference paper which is titled "An Image is Worth 16 by 16 Words, Transformer for Image Recognition at Scale." So the innovation or basic idea is coming from the transformer architecture, which is originally designed for natural language processing, and they use that idea to implement in images. So the key idea is here, instead of using convolutional operation, it treats images as sequence of patches and classify them with self-attention mechanism. So what are the differences between convolutional neural network and vision transformer? So first of all, the input of convolutional neural network are raw pixel values. But for vision transformer, it divides input images into patches and transform them into tokens. The processing mechanism also are different. For CNN, use convolutional and pooling layer to hierarchically capture features, but for vision transformer, it employs self-attention mechanism to consider relationship among all patches. And for CNN build global context gradually through hierarchical layers, but in vision transformer, it inherently capture global context through self-attention and early layers. And the induction bias, it is also very important. In CNN, is strong inductive bias for spatial relationship through convolutional operation. But in case of ViT, the minimum built-in induction bias learns parameter directly from data. Those are the main differences between a traditional convolutional neural network and a vision transformer. So let's understand the architecture of a transformer first, then we will move into vision transformer. So the main focus in transformer that it uses self-attention mechanism. So here, as you can see, we have a architecture on the right side of this slide. So this is called a encoder, and this one, the right figure, it is a decoder of a transformer network. Here first it uses a self-attention mechanism that weights the importance of each element in a sequence relative to each other. It also uses multi-headed attention. So this multi-headed attention is multiple parallel attention heads that learn different relationship. So it uses here. Then it uses a feed-forward network, so that processes the attention output through fully connected layers. We also have a normalization layer which stabilizes the training, and it also has residual connection, helps gradient flow during the training process. So this is overall an idea of how the transformer works, or what is the transformer architecture. The same architecture is used in vision transformer, but instead of using the word or letter, here we input an image, but first we divided the image into fixed patches. So this part here, you can see this image is divided into fixed patches. This operation is called patch embedding. So usually it divided the images into 16 by 16 patches. That means each patch contains 16 by 16 pixel data. So when we perform this patch embedding, we will get this patches of information from a single image. Then it processes through a linear projection. So transform patches into embedding vectors. So it is converting these patches of data into a vector data, embedded vector data. We also input a class token. So right here we also input a class token along with this. Then we also have a position embedding. So here it is the position embedding added to patch embedding to encode spatial information. So it gives the information of each patches and its position in that same image. Then we have a transformer encoder. This transformer encoder is also shown on the right side here. So this transformer encoder have multiple layers of multi-head self-attention and feed-forward network. So the input of this transformer encoder is the embedded patches. Then you see it has a multi-head attention followed by normalizations and then the MLP. So and then we also use the link for residual connection. So this is one block of transformer encoder. We can use multiple block. So then finally we use a MLP head, and which is like final classification layer. Then we can get the classification output. Next, let's talk about how vision transformer work actually. So this patch embedding things, as you can see, we divided into non-overlapping patches. So this is one single patch. So we divided the image into non-overlapping patches. Then create a sequence of flattened 2D patches using that each patches here. So here you can see we have, if we take a image which has a resolution of 224 by 224, and these three represent the, if we use a color image, then it has a RGB 3 plane representing it. If we divide it into 16 by 16 patches, then we will have 196 patches here. So to obtain patch embedding, each patch is then linearly transformed into a vector using a learnable linear projection. So there are some parameter in training. This parameter is also learned by the network. Moving forward in the position encoding, so in transformer there are a permutation, invariant and positional information must be explicitly added. So linearable position embeddings are added to patch embedding. So this information is also added on top of patch embedding. Helps model understand the spatial relationship between patches. So for instance, if it is the first patch and let's say this is the fourth patch, so what is the relation between these two patches? It is learned through this position encoding. Then we also has class token. That means if we performing a image classification task, then each image has a class. So then we give this class token in the training phase. So this is also like a special learning embedding class token pertain to the sequence. So it is given into that same sequence. So output corresponding to this token is used for image classification. Moving forward, when we describe about the transformer encoding, as you can see, it is a sequence of patch embedding plus class token. So the input of this transformer encoding is the sequence of patch embedding plus the class token we provided. And as I mentioned, it has normalization layer followed by multi-head self-attention layer. Then we have a feed-forward network. So here it is. So this is about the transformer layer, where it learn the relationship between each patches and also the class token. In step 5, so in the classification layer, we have a MLP head, and this MLP head produce the final classification prediction. If I talked about the performance and results, so the key findings we can summarize as the vision transformer outperform state-of-art CNN, especially when it is pre-trained on large data set, and it requires like 2 to 4 times less computational resources than ResNet for similar performance. Also, it shows strong transfer learning capabilities for downstream tasks. So for a small data set, it is very important. CNN perform better due to the inductive bias, but for a large data set, ViT outperforms CNN. So the next question is, what ViT model actually learns? So first, these self-attention layers, even in early layers, some self-attention head can attend to most of the images and demonstrate ability to integrate information globally from the start. So this self-attention layer gives a step ahead. So it can start learning the global information from the start. The positioning embedding model learns to encode relative positions of patches. So it learns the information, the relation between the information of different patches. And finally, the linear embedding filter capture both low level feature like lines, edges, and high level patterns. Attention map show focus on symmetrically meaningful part of images. This is also very important. Now let's talk about application of vision transformer. So from the beginning, as I mentioned, it can be used to classify images. So it is a supervised learning, classify images into predefined categories. It can also be used for object detection, identifying and localize object within the image. It can also be used in segmentation, like assigning a label to each pixel in an image to identify object boundary, and also in image generation, generate new images based on a given context or description. So these are the applications. So its applications are very wide and it is used in every field of computer vision. So finally, I like to conclude with some limitation of vision transformer. So as I mentioned, training a vision transformer effectively often requires very large data set. So it works better if we can provide a large data set to train. which might not be available for all domains. So this is a kind of limitation. And the computational demand, like the training ViT, can be computationally intense due to the self-attention mechanism. It learns more parameter than a convolutional CNN, like traditional CNN. And the spatial information, the ViT sequential process might not capture fine-grained spatial patterns as effective as CNN for the tasks like segmentation. So if you are looking for fine-grained information, spatial information, in that case CNN works better than vision transformer. So those are some limitation of vision transformer. Thank you for listening. We will come back in another video.